In this module, we will discuss the heat effects associated with chemical reactions. There are two kinds of changes that we need to consider during a chemical reaction. First, there are the chemical changes. This involves reactants turning into products. Second, there is another type of change, the heat effect. This heat effect is important because it is a physical quantity that can be measured experimentally. There are no tools that measure the energetic properties of chemical substances, such as internal energy or enthalpy, directly. By measuring the heat of chemical reactions, we can deduce associated changes in internal energy or enthalpy from experiments. So, we will focus on the heat effect of chemical reactions. We quantify the progress of a chemical reaction using the extent of reaction Xi. In this module, we will focus on reactions under constant pressure, which is a typical scenario. At constant pressure, the infinitesimal amount of heat exchanged in a reaction, denoted here as delta Q pair, as a function of the extent of reaction Xi, equates to the change in the system's enthalpy, represented by dH. In other words, as the reaction progresses at constant pressure, the heat produced or absorbed is equivalent to the change in system's enthalpy. To further understand this, we consider the enthalpy change between two states during the reaction. When we take the derivative of this change with respect to the extent of reaction, we arrive at what we call the reaction enthalpy, denoted as delta RH. The reaction enthalpy can be described as the change of the system's enthalpy associated with the chemical change equivalent to the advance of the extent of reaction by 1 mole. Note that the dimension of the reaction enthalpy is energy per amount of substance, and its coherent SI unit is joule per mole. Now, let's start with some definitions. An exothermic process is one that releases energy in the form of heat. On the other hand, an endothermic process is a process where energy is absorbed from the surroundings in the form of heat. Now, a fundamental question arises. When do we describe a chemical reaction as exothermic or endothermic? You might know the answer, but understanding the underlying reasons is also important. As the chemical reaction progresses, the system's enthalpy changes. This change is equal to the reaction enthalpy multiplied by the change in the extent of reaction. If the reaction enthalpy is positive, the enthalpy of the system increases in the course of a reaction. According to the first law of thermodynamics, this change of energy cannot come from nowhere. It must come from the surroundings. The surroundings must deliver the amount of enthalpy equal to system's enthalpy change, and it is delivered in the form of heat flowing into the system. Consequently, this reaction requires an input of heat to proceed and is an endothermic process. On the other hand, if the reaction enthalpy is negative, the enthalpy of the system decreases during the reaction. The decrease of system's enthalpy must be released into the surroundings in the form of heat. This reaction produces heat and is characterized as an exothermic process. How can we determine the reaction enthalpy? It is not as straightforward as calculating the difference between the total enthalpies of products and reactants. Why not? Because the absolute enthalpy value of a substance is immeasurable. To address this, a relative scale of enthalpy was introduced, quantifying it for chemical substances. This scale utilizes a physical quantity we refer to as the enthalpy of formation. Specifically, we will focus on the standard enthalpy of formation, represented by the symbol delta FH standard. The reference state of this relative scale is defined as follows. By convention, the standard enthalpy of formation of elemental substances at the standard ambient temperature and pressure in the form that is the most stable at SATP and in their standard state is defined as 0. This definition gives us a reference point from which we can determine the enthalpy of formation for any chemical substance. Now, what exactly is the standard enthalpy of formation of a chemical substance? In its strictest sense, the standard enthalpy of formation for a substance is defined at SATP. It represents the change of enthalpy during a reaction wherein a substance in its standard state is formed from elemental substances which are also in their standard state at SATP. When discussing the standard enthalpy of formation, we must always specify the physical state of the substance in question. Individual physical states of the same substance are characterized by different values of standard enthalpy of formation. The physical state is denoted as S for solid, L for liquid, and G for the gaseous state. These specific values, the standard enthalpy of formation in its strict sense, are the data listed in reference sources. The term standard can also be applied in a broader sense. The enthalpy of formation can be regarded as standard when it refers to substances in their standard states, irrespectively of the temperature. If you aim to determine the standard enthalpy of formation of a substance under conditions other than SATP, you will need to consider the additional state changes for that substance after it, so to say, has formed from elemental substances. This indicates notably that the standard enthalpy of formation for elemental substances is not 0 when the temperature is not at the standard value. How can we calculate the reaction enthalpy, specifically standard reaction enthalpy? The term standard reaction enthalpy, delta RH standard, describes the reaction enthalpy determined when all reaction participants are in their standard states. If you want to calculate this reaction enthalpy for a particular reaction, you start by finding the standard enthalpy of formation at SATP for every participant in the reaction. These data can be sourced from various reference materials. However, if the temperature of interest isn't the standard temperature, then we have to account for the changes in molar enthalpy caused by state changes. First, there is a change in temperature itself. The associated change in molar enthalpy can be calculated as the integral of the molar heat capacity, CPM, with respect to temperature taken between the standard temperature and the desired temperature. We might also have to account for changes in molar enthalpy due to the phase transitions that occur during the state change from the standard temperature to the desired temperature. Finally, to calculate the reaction enthalpy, we use the stoichiometric numbers of each reaction participant. The standard reaction enthalpy at a specific temperature T is found by summing up for all participants their stoichiometric number times their standard enthalpy of formation at that temperature. The stoichiometric numbers for reactants are negative. This is why this equation can also be interpreted as the standard reaction enthalpy equals the total standard enthalpy of formation of products minus the total standard enthalpy of formation of reactants. This calculation method is valid because standard reaction enthalpy is a state function. The value of the standard reaction enthalpy for a particular reaction solely depends on the initial reactants and the final products. We can combine reaction enthalpies for several reactions in the same way as we combine the reactions themselves to achieve the desired reaction. This is what we are essentially doing here. We use the standard enthalpies of formation as building blocks to derive standard reaction enthalpies for other reactions.